Thank you for joining today's webinar where we will guide you through tasks you can perform and information you can retrieve from data collected through our latest TrueView 645-650 sensors and the DJI Matrice 300 RTK system. My name is Rebecca Perry, the Manager of Marketing Communications here at GOQ, and I'll be hosting today's webinar. To start, I'd like to review the agenda for today's presentation. We'll begin with an introduction from our CEO, Frank Darmian. Then we'll proceed to a quick look at what you can deliver by using our LP360 software with data collected from the 600 series and DJI 300M. Next, we'll conduct a product overview of the 645-650, followed by the mechanical and technical specs of the sensors. Then, DJI has provided an overview of the Matrice 300 RTK, and we'll conclude with a closer look at processing data in LP360. Today's presentation will last about an hour. Therefore, in consideration of your time, please submit any questions in the GoToWebinar chat on the left-hand side of the screen, and we will have a response for you within 24 hours. Now, to begin, I'd like to introduce the CEO of GOQ, Frank Darmian. Welcome, Frank. Can you give us a little overview of the TrueView 645-650 sensors and explain who they're for?
Sure, yeah, thank you very much, and welcome to our TrueView 600 series webinar. So DJI came out with the M300 about a year ago, and the question we asked ourselves was, how can we get our higher-end LiDAR payload, which at the time was the 615, that carries a Regal Minivox 3, an Apex 20, and a dual camera. How do we get that on the M300? And of course, the big challenge was the weight. Is how can we get it light enough? And so we didn't want to compromise. We felt that the dual camera system is what we need to colorize the full 120-degree field of view of the LiDAR. And we didn't want to compromise on the GNSS INS system as well, the APX20, which is, again, what we think is appropriate for a sensor of that quality. So we went back to the drawing board, and we come up with a all new power management system to supply the unit. We came back with a new computer, a new CCU unit, the brain of the system, and we had to rethink the entire assembly of the payload just to fit under the 300 and to match the weight we had available. And of course, that entire package will work with the LP360 software that guides the user through the post-processing, helping the user do the trajectory correction, the geocoding, the colorization, just like with our previous system. But it's now in a form factor that fits well under the M300.
Thank you very much, Frank. Next, to give you an idea of what's in store when you put the 645-650 to work, let's start with our end product in mind. Martin Flood, our Vice President of Special Projects, will give us a peek at a point cloud visualization and where you can go from there in LP360.
So I want to take just a couple of minutes to show you some of the outputs you can get from a 645 or 650 when you're flying on an M300. So I'm just going to show you a data set from our test and calibration range in Huntsville. And I've already processed all the data. I'm just going to focus on some of the outputs, some of the things that you can get from the data. This is 645 data, so it's the Regal Minivox 3 paired with the APX15. Flown on the DJI M300. And you can see here I've got the colorized point cloud. I actually have a Bing map in the background. I'll turn that off because it's just a little bit easier to see. So of course, one of the major outputs is your LiDAR point cloud, your LAS data. We automatically colorize that from the oblique camera. So I have the colorized data here. Obviously in LP360, you can display this in a variety of ways. We can have the traditional elevation view which many I'm sure of you are familiar with. This data has been classified. That's a key value add that you can do to the data. So I've run a ground classification. I've run a height segmentation to get the above ground, the vegetation, low, medium, and high canopy, and also classified out the two main buildings that we have in this site. Now, of course, before you start generating some deliverable product, one of the things that you'll want to do really quickly is check the accuracy. We can do that quite easily in LP360. I do have a set of checkpoints that I've brought in here, and we have a tool that we can run just to generate a standard ASPRS report of the accuracy of these checkpoints against our LiDAR surface. And this is a standard tool that you can use in LP360 for any LiDAR data or point cloud data when you want to verify against control. I'll go ahead and run that test. We're measuring from the checkpoints to the control surface. When you have some systematic remaining residual bias in your data, we have a tool that'll let you take that out. So you can see that essentially I've debiased my data and I'm left with an RMSE of just right around 1.5 centimeters. This is in meters. My map units are in meters. So you get about 1.5 centimeter accuracy data set. It's very nice for being able to assess that accuracy and report that to your client. Now, of course, I have other views that I can use just for visualization. I've got some standard isometric views where I can look at the data, zoom in, zoom out, rotate around, and so forth. And of course, the very ubiquitous profile view. So I can see a slice through my LiDAR data. I can check on my ground classification, my height above ground, my vegetation classification, and these are all classified to the standard ASPRS class codes. We have an export wizard that helps you derive some of your or generate some of your deliverables from the data set. There's a lot of different options here, and just for time, I'm not going to go through them all. I'm just going to show you some of the outputs. But basically, you can choose whether you're outputting points or surfaces. If you're outputting rasters, you can generate DEMs, hillshades, contours. Lots of different options here for the kind of output products that you might want to generate from your LiDAR data. I'll just show you a couple of these. So I did generate a DEM. So essentially, this is the bare earth ground classification, including the building roofs, because this is a DEM that I can feed into my ortho production process, into my generation of my ortho photo. So that's quite nice to be able to do. That generates very quickly from the data set. And of course, contours. Let me change my view back to colorized point clouds, so those will stand up a little bit better. So you can generate those contours either for display purposes or output them as a CAD file or a shape file. Now the DEM that I generated, I can pass that into Metashape for Evo, which is our licensed version of Agisoft's Metashape to generate the ortho photo from my oblique images. And that works out very nicely as well. I do have that ortho here. It's a slightly larger collection area for the cameras, but we can see if I turn this off. So I have my ortho in here as well. So in general, that's a quick overview of where you can go starting from your colorized point cloud. You can do a quick accuracy check to make sure you're meeting your accuracy standards, and then you can, of course, classify the points into different features. So we did a standard ground classification here. Generate contours, generate DEMs, and then flow the data into more value-added work downstream. So we have tools in LP360 to let you take your TrueView data and do, for instance, wire extraction for power line, transmission line work, volumetrics for stockpile work, rail extraction if you're doing rail networks, and so forth.
Thanks for the quick demo, Martin. We'll get back to you shortly for a more in-depth look at end-to-end processing. Next, I'd like to introduce Chad Dillard, our Technical Manager for UAS Operations, who will conduct a product overview of the 645-650.
All right, thanks for having me. And my name is Chad Dillard. I'm going to do a brief technical overview of the TrueView 645 and 650 sensors, talk about some of the details that are kind of unique to this sensor and what makes this sensor stand out from others. So real quick, just kind of define some terms for us. So the 645 and 650 is a 3D imaging sensor, or 3DIS. This means it's a fused LiDAR and photogrammetric camera solution all tied together. So all of our TrueView line, the 435 and 515, those are 3DIS. The 600 series, the 645 and 650, those are 3DIS. And then we also the DJI ZenMuse L1 is also a 3DIS. So 2DIS sensors that we support, being their photogrammetry only with no LiDAR. So the Phantom 4 RTK, the M300 with a P1 camera, and then the M210 RTK with the X4S camera. All right, so the 645 and 650 cameras come with two RGB cameras, and these are important because it allows us to maximize our efficiency. So two cameras mounted 25 degrees off nadir. So you've got one camera looking port side, one camera looking to the starboard side. And they're 20 megapixel RGB cameras with mechanical shutter. So we had these purpose built for mapping. Lens, 128 millimeter lens, fixed focused. And so they are assembled to produce 120 degree total field of view, and that's to match our LiDAR. So kind of to explain that, so we got two diagrams on the screen here showing a LiDAR system with a single nadir camera. And you can see from the legend here at the bottom, so the red triangle represents the LiDAR field of view, black triangle represents the camera field of view, and you can see that the camera field of view, unless you're using like exceptionally large wide-angled cameras, is going to be far less than, it's not going to cover the same area as your LiDAR. So if you're trying to collect imagery and LiDAR at the same time, trying to collect imagery in a manner that would allow you to generate a good orthomosaic, you really need a certain amount of overlap between photos. And so to do that in a single camera setup, you have to fly your flight lines much closer together, and you're losing out on that efficiency that LiDAR provides, at least in the width. So on the right hand side, we have a TrueView 645, 650 dual camera setup. And so you can see now with the two cameras, I'm able to capture the entire width of the LiDAR swath with my two cameras, and even having the cameras overlap some there in the middle. So what this lets me do is I can maximize my flight plan so that I'm creating a flight plan for the LiDAR and not for the imagery. And so I can space my flight lines further apart, meaning I can cover a larger area in a similar flight time. So that's the benefit. There's in a single flight, I can cover more area than I can with just a single camera if my goal is both LiDAR and photogrammetry or an orthomosaic. Okay, let's talk about the scanner. So this is a Regal Minivux 3 UAV. This is their 3rd gen UAV sensor. So this sensor was designed to be able to collect data up to 300 kilohertz or 300,000 pulses per second. It also supports up to 5 returns per pulse, meaning we can get 5 return values from a single LiDAR pulse, and that gives us better penetration, which I'll show here in this chart. So on the right hand side, I've just got a screenshot of a 645 point cloud over a concrete parking lot. And we're just showing this is one of our point cloud statistics here. We're just showing the point density of this area in a points per square meter. So 115 points per square meter, and that's that's 300 kilohertz setting. So in the that's still quite dense. That's very dense. So 10 points per square foot. That's sufficient for almost any topo project. And then obviously that's flying at our recommended settings. So this is flying at 70 meters here with 5 meters per second flight speed. So the system also can support up to 5 returns, as I mentioned previously. So if you're unfamiliar with what a return is, so when the LiDAR creates a pulse, sends out a beam of light, and it strikes an object, it gets a return from that pulse. And so if there's enough energy left, it will continue to the next object, gets a pulse, and then continue to the next object, another pulse. So this system can get up to 5 pulses. And so what that does is it increases the amount of opportunities you have to get through that canopy to the ground and get ground points, which is in the vast majority of use cases, is the goal, is to get good ground coverage underneath the tree canopy. And then finally, the third component that the big one on this one is, one of the 3 important components is the position orientation system. So the 645 has the APX15, while the 650 has the APX20. So the position orientation system, basically, it's as as described, it provides your position and then the heading, roll, and pitch values that allow us to properly position the LiDAR in the world. And so obviously the quality, the accuracy of those values, the heading, roll, and the pitch, determine the accuracy of our final point clouds. It's important to have a good position and orientation system. So that's why we went with the APX15 and APX20. So with the APX15, you're looking to get accuracy-wise 3 centimeter root mean square, and precision the 2.5 centimeter at 1 standard deviation. So when you bump up to the APX20, it has another external orientation sensor on that, a more precise one, so that you're going to have an increase in accuracy. So the accuracy of 2 centimeters, and then precision of 2 centimeters at 1 standard deviation. So that's the kind of the items that differentiate these sensors and make them the best in class LiDAR sensor. So all right, so that's the kind of the technical overview, and I'll turn it back over to you.
Great. Thank you for your presentation, Chad. Now, please welcome Colin Adair, our Director of Payload Production, who will help explain why the 645, 650 are a great fit for the DJI 300M.
All right, thank you very much. A little back history on how the TrueView 645 and 650 came to be. We have a TrueView line of sensors that is a 3D imaging system that started with the TrueView 410 back in 2019. That came from a Loki system that was a PPK system that used photogrammetry, 2D imaging to form 3D images. Then we coupled it with LiDAR in 2019. The TrueView 410 sensor was the first sensor that we produced using LiDAR and 2 stereoscopic cameras. After 2019, we created the 615, which is the first sensor with the Regal. This is the first TrueView unit with the external IMU. The 620 has the external IMU, and the 615 has the APX15. Then in 2021, we had 3 sensors come out, a variation of the 615 and 620 with an upgraded Minivux 3. The Minivux 3 is important because it spins much faster than the Minivux 1 and 2. So you're able to get a lot more points and a lot denser point cloud as a result of that. The 515 and 435s were iterations of the 640. And then in 2022, we came out with the TrueView 645 and 650. These are just lighter versions of the 635 and 640 systems. We saw the need to produce a lighter version to fly on the DJI M300. The lighter versions were achieved by reducing the self-powered battery module, and it's powered from the drone, directly from the drone, and not sacrificing flight time by doing so. And like I was saying, pulling power from the drone, we did not see a lot of reduced flight time, but we're able to accept a wide power range, 12 volts to 36 volts. And pulling from that, we can integrate with various drones, not only just the DJI M300. But this sensor was geared around flying on that DJI M300. The DJI M300 has a payload capacity of 2.7 kilograms. So we had to come in underneath that payload capacity with a mounting kit. We have our mounting kit is our standard TrueView mount. It's a DJI Dovetail based on a DJI Dovetail mount. The Dovetail mount is crucial because it's a self-locating mount, so it's repeatable, easily to remove from the drone without any hand tools, and then also the redundancy of a failure mode. You have it will not fall from the drone in a failure mode. So we have a tether, a secondary tether to the drone. So this slide shows a Regal Minivux 3 with the dovetail mount, and then the Google TPU CCU. So that Google processor is what we use to process all the data during flight. It's collected via a USB data stick mounted in the sensor itself. And then we have the two IMUs. It's the APX15 and the 645, and then the APX20 with an external IMU called the IMU90 in the 650. And then the two cameras are mounted in a 25-degree angle opposite of each other. This allows for a wider path and more overlap between flight lines when flying. If you will notice, it's different from other TrueView sensors in that it doesn't have an internal battery compartment. This was due because the design required a reduce in weight, so we could not fly with an internal battery. We just have two ports. One port pulls power from the drone, and then the other port pulls a GNSS signal from the antenna. Here is a comparison of the 635 and 640 sensors to the 645 and 650 sensors. As you'll see, they're the same hardware, but in the lower rows, you can see the reduction of weight that was achieved with reducing the amount of metal components and the battery compartment. We're still able to get a 30-minute flight time from the M300. That's in ideal conditions. So you can expect to see the same amount of flight times as you would with a TrueView 515 as this unit. And note here that the weight is only the sensor. The total takeoff weight for a 645 on an M300 is 2.5 kilograms, and the total takeoff weight for a 650 on an M300 is 2.6 kilograms. So here we have the close-up of the two cameras that are mounted 25 degrees off nadir, as Chad mentioned in his presentation, that this provides 100 degrees in cross-track field of view. These two cameras are mounted to an aluminum rigid frame that helps keep their position as they are calibrated here by GeoQ from the factory. This calibration's essential to bore sighting those cameras to the laser scanner. And you'll see that in the 645 and the 650, we still maintain that rigid aluminum frame to mount the IMU to on the back of the Regal scanner. This image shows a 410, but we incorporate that same aluminum frame in the later generations. Here we have a close-up of the sensor mounting to the dovetail. The TrueView sensor slides onto the dovetail from the side. So at a pitch and roll, we're clamped securely to that dovetail. That's an aluminum frame on the sensor that's rigidly mounted to the Regal scanner. It's really easy to slide the system on and slide it off from the side. This allows the user to not have to use any tools in the field to attach the sensor. We recommend a stainless steel safety cable be also attached as just a safety. This is included with every system that we sell, and it's just a redundancy in case of a failure. The UMS, as we call it, is a 3.0 USB drive. This is what's used to extract the data from the system after each flight. This also holds all the system configuration files. So if you were to fly it on a different drone or another platform, you can update the Applanix GNSS lever arms on here, as well as other settings through this system configuration file. This allows the user to really customize and control what configuration the sensor is. We also pre-configure the systems as they will be flown from the factory. So it's set up as you purchase it. If it's going to be flown on an M300, it's set up for an M300 as it leaves the factory. So thank you for allowing me to present today. It's a pleasure to be able to demonstrate why the 645 and the 650 are a good fit for the M300 drone. There's not any other offering on an M300 that couples the Regal with cameras. You're able to fly one mission and capture imaging and LiDAR data at the same time with a small platform such as the M300. Thank you very much.
Thank you, Colin. Next, DJI has shared with us an informative presentation on the Matrice 300 RTK, hosted by their DJI Enterprise Solution Engineer, Grant Hustica.
Great to be with you all here this morning. The M300 RTK is continuing on the standards set by DJI over the years in both product safety and product security, including altitude limitations, flight distance warnings, obstacle sensing, AirSense ADS-B, and then on the product security side, the option for operators to use local data mode or AES-256 encryption for the transmission from the RC to the drone. Alrighty, getting things rolling on the performance side. One of the first questions everyone wants to know, what's the flight time? So, without a payload, you're looking at a 55-minute max flight time, which increases the previous max flight time with a 210 V2 RTK by 140%. Now, if we're talking about effective flight time here, and just how this was calculated here, effective flight time would be landing the drone with 7 minutes left. So the effective flight time of the M300 RTK with an H20T would be 36 minutes. If you're looking at total flight time for the M300 RTK and an H20T, you're looking at 43 minutes. So hopefully that makes sense there, but I think many of those with standard operating procedures would say they're not going to attempt to land the drone with 0 minutes left of flight time. So that's where this effective flight time comes into play. And if you compare that to the M210 RTK V2 with an XT2 and a Z30, you're looking at 15 minutes of effective flight time or 22 minutes of total flight time if you were to land it, obviously with no battery left. But ultimately, when you see the calculation there, landing with 7 minutes of battery left, you're looking at more than double the flight time with this platform compared to its predecessor. The fast charging battery station is an all-in-one charging and storage solution. So you can place 8 TB60s and 4 WB37 batteries in the charging case. WB37s, many of us know those as Crystal Sky batteries, small black batteries that will go in the Crystal Sky itself or a DRTK2. In this instance, those WB37 batteries are hot swappable on the Smart Controller Enterprise. This provides a solution to charge both of those batteries. If you put 8 TB60 batteries in, it would go ahead and charge the 2 that are closest to 100% logically. So if you put a bunch of sets of batteries in, the highest ones are at 40%, it'll charge those first. To charge 2 batteries to full capacity, you're looking at 60 minutes or 70 minutes with 110 volt inverter. Here in the US, we're looking at 110 volts, so you're looking at 70 minutes to go from 0 to 100. And ultimately, you're using the battery station here to enable continuous flight, where you're able to fly and you're able to charge. You also have the ability to upgrade the TB60 batteries in the battery station itself. We can connect the RC to the battery station. There's a USB-C on it right next to the power button. And then from the RC, you can upgrade all 8 batteries at one time. So really saves you a lot of time in that regard, where its predecessor, the M200, you had to individually put the sets of batteries onto the drone and refresh the firmware. In this case, you can open up the Pilot app and update the firmware of the batteries through that. Safety and reliability of the platform. As we talked about, there's 6 directional sensing and positioning on the drone itself with those visual and TOF sensors. It has up to 131-foot max detection range. And a very nice feature is that you can customize the aircraft sensing behavior. So you can customize the braking distance. So say I set my braking distance to 10 feet and there's a wall or a tree, or an obstacle in front of me, and I'm trying to push that right stick forward. If you're flying in mode 2, as many of us would, the drone is going to stop and not proceed forward when it's 10 feet away from the obstacle. Now you can also set a sensing distance where it'll show up on your navigation display in yellow, and you say, okay, there's an obstacle that I've set in my 20-foot or my 40-foot range, and I know it's there, but I don't want the drone to be stopping when it's sensing an obstacle at that distance. So it really gives the operator a lot of customizability there. And you can customize the horizontal sensors, the top sensor, and the down sensor. So 3 different options you can do there. Also has top and bottom anti-collision beacons. If you're using the drone and need to satisfy the condition for a daylight waiver, and top and bottom auxiliary lights as well. UAV health management system, another great feature that's been added with the aircraft here. First off, you have your health status monitoring. So you can see on the screen in our example photo here, the avionics tab has a warning on that. So the user could go ahead and click on that tab and quickly determine what's wrong with the module according to the warning there. If they see green, obviously that's good. If they're seeing yellow, use caution. You can look at the warning or information there as well. Flight data management records the aircraft's data, such as total flight duration, total flight time, total flight distance. And then what's great is you can use that total flight time to follow through with maintenance suggestions with the aircraft accordingly. But with the DJI maintenance program, you want to keep track on how many total flight hours you have, so you can go ahead and get the proper maintenance done at the proper amount of flight hours. Flight log management can easily export remote controller logs for post-flight analysis. And then firmware management. As we talked about before, you can upgrade the batteries by connecting the RC to the battery station here. You can also upgrade components as well. Air records and troubleshooting guidelines. What's great here is if you do a flight, you're focused on flying the aircraft itself, having a safe flight, as a pilot should, and you see a warning come up during flight. When you land the aircraft, you can go into the health management system here and see what that error message was and look at the help document to get some more information as well to see if there's something that needs to be done, or what steps need to be taken in regards to the error message that you received. Redundant systems of the aircraft, first one being multi-sensor redundancy, dual IMUs, barometers, compasses, RTK antenna, and GSS module. Advanced dual control of the aircraft itself. So now both RCs connect to the drone directly. So you're going to have to go ahead and pair them before takeoff. But then in air, a second controller can immediately take control of the aircraft with the click of a button. And just on the safety and security side, it's not like the drone is up in the air looking for a remote controller to connect to. It's the same process you use to pair your aircraft to a remote controller right now, except that you can pair up to 2 remote controllers. So it still uses our AES-256 encryption during the transmission stage. Both RCs are directly paired to the aircraft. Just allows you to do a lot more on the mission side, which we'll cover later, and then also another redundant system during flight. Dual batteries, as you can see here, if the event one battery fails, the drone can still return home safely. Another safety feature with the upgraded flight controller is the 3-propeller emergency landing. Gives the pilot the opportunity to maintain control of the aircraft, especially in the case of a motor malfunction. And this is a really cool video here. And when this occurs, the RC will alert the user by vibrating. And then ultimately the user can land the aircraft onto a safe zone by controlling it during the spinning descent you see here. And ultimately, during this emergency situation, helps to reduce the chance of the aircraft and payload dropping and damaging anything directly below it. Gives the operator the chance to put it into a better spot. As you can see there at the end of the video there, sticks down and in. That'll allow the aircraft propellers to stop as well. The drone also has an extra wide FPV camera to help maintain situational awareness, even if for some reason the camera payload isn't functioning properly. ADS-B receiver. Drone has an ADS-B in receiver. So if there's an aircraft with an ADS-B out in the area, you'll be able to see that within the DJI application. And it also prioritizes those ADS-B inputs as well. So if something's closer, I believe it's within a mile, it's going to show up as red on the screen, just so you can be aware as the pilot in regards to other air traffic in the area. Rounding up a few specs here. The diagonal length of the drone is 35 inches. You can see it folds up into a bit more of a square shape than a rectangle of its predecessor, but is a bit bigger when unfolded as well. Weight-wise, we covered max flight time, 55 minutes without a payload. Max speed, 51.4 miles an hour. Max ascent and descent speed. If you need to get somewhere fast, you can put it in sport mode and utilize those. Max service ceiling, 22,965 feet. Max wind resistance of 33.5 miles an hour. Supports the H20 series, the Z30, the XT2. IP45 protection. Operating temperature of -4 to 122 degrees Fahrenheit. And max transmitting distance up to 15 kilometers using the FCC. And you can see there, we have the M300 RTK aircraft, the battery station, Smart Controller Enterprise, which you can put those WB37s and batteries in the back, keep yourself running, and the TV60 intelligent flight batteries as well. Alrighty, thanks for taking some time out of your busy days to join us with the M300 RTK.
Great product information provided by Grant. So now let's take a look at the data when you pair the DJI 300M with the 645-650. Please welcome our Vice President of Special Projects, Martin Flood, to review data processing in LP360.
Okay, so this is the end results. This is where we have our output products, our classified point cloud, our contours, our ortho photo, and so forth. But I want to walk you through briefly the actual process to arrive at that, to show you how it's streamlined and fairly seamless within the LP360 environment. So Once you've gone out and flown and collected your data, so you've done your 645 or your 650 flight on your M300, you've downloaded the data from the unit, and you have that ready to process. That can be on the field. You can process in the field on your laptop or bring it back to the office. You're going to go ahead and you're going to import the cycle. So cycle is the term we use for a flight or a mission. So I'm just going to go ahead and just do an import here only, just to walk us through the process. And so when you download the data, you're going to have a cycle folder, and you'll go select that. It'll automatically point to both our raw LiDAR data, our bin data, and our raw imagery. I can come in here and I can add some descriptions, some area names if I want to segment or separate out my cycles by different areas of my site, or just include some description of the area. And I also need to set a spatial reference system. In this particular case, this is already set to Alabama East because I know that's where I'm going to be. I need to read in my base observation file. If I have that already, then I can browse out and select that, or it will be part of my archive. And then I can include any ancillary files or additional files. So this could just be any additional information I want to include. And I do need to determine if I'm using a local base station, where my local base station was. So I have a base station a catalog, or a survey nail catalog, where I can store commonly used reference points if I'm flying my same location over and over again. If I was set up on a new point and I have an Opus report, I can pull that in to get the information there as well. And of course, I can also just enter the information if I have that. And add a new reference point to my survey nail manager. And then I go ahead and finish that. I'm not going to actually run that just for time purposes. What that will do is generate several layers in my map, and I'll turn them on here, that basically represent the cycle, the flight that I just flew through. And we'll just zoom in a little bit on that so we can see that. So I have here the basically the photo center, so the camera stations for my images. Those are the dots we see there. I have my trajectory points. That's the real-time position of my system, the M300, during flight. And typically where we start is we want to run through and do the pause pack processing. So we use the Planix APX15 in the case of the 645, the APX20 in the case of the 650 for our position and orientation solution. So this is where we're going to combine our GNSS data with our orientation data to get our refined trajectory, our precise trajectory and pointing information for our system. Again, I'll just walk through this quickly so you can sort of see it. There's obviously a fair bit of detail in here, but essentially I have two options. I can run with a local processing. If I have PausePack Desktop, I can run in PausePack Cloud. If you're using one of our subscription or rental systems, you will be using PausePack Cloud. I can run in one of several processing modes, a local base station or single base station, which is typically the recommended and most common way people will run, is when I have a base station set up near my site. But I can also use Planix's Smart Base, which is their VRS, Virtual Reference Station system, or Trimble's PPRTX Global Positioning System as well. I do need to provide a little bit of information. Again, the base station observation file. It will know the survey nail, so my reference location for my base station that I've set up, and my output reference frame. It'll give me a little bit of information about this, and then I can go ahead and submit this. And it will essentially run PausePack, either local on my desktop or up in the cloud, and essentially generate my refined trajectory, my post-process trajectory, which gives me my more accurate positioning and orientation of my system. Again, for time purposes, I won't actually run that now, but it does generate the standard PausePack report. So you have access to all of the details, great details here if you really want to dig down into the technical aspects of, what's going on with your position solution. Does require, of course, some understanding of this. It's quite detailed engineering and technical information about what's going on, but we have all that available for you, so you can check on the quality of your positioning, because of course that's critical to getting good quality, both point cloud data from the LiDAR and positioning for the imagery. So once I have my pause pack step run, once I've created my trajectory, I do want to create my flight lines. So this is where typically I'm going to take the real-time trajectory points and create the actual flight lines where I want to process data. And there may be areas of my flight that I'm not particularly interested in. There's transit legs here, there's takeoff and landing sections, there's turns. So we have an auto create tool that'll try to automatically remove those for you. Once I have these trajectories, I'm going to go ahead and run the next step, which is to create what we call our TrueView trajectories. A little bit of a similar sounding name, but basically what we need to do is take that post-process trajectory we got from pause pack, so the refined position and orientation information, and essentially match that with our desired flight lines to come up with a trajectory where we're going to actually process the LiDAR data and update the camera information. So this particular dialog lets me set up for that. Again, I won't necessarily go through and run it, but I will kind of explain what's going on here. Obviously, we've got to have that post-process trajectory file. Since I had run pause pack, I already have that in my project. A calibration file is maintained for every TrueView unit. And of course, this is important for TrueView or for any LiDAR system. There's always a set of calibration parameters, bore sight and systematic errors, and so systematic offsets and lever arms and so forth, that you need to input to your software to ensure that you're getting accurate data. It needs to have the proper reference system and the proper positioning of the sensor in that reference system to give you the accurate data that you want. So there's a calibration file. Those are maintained through our Reckon web portal, and you can sort of see here the software is it knows the serial number of the unit I'm working with. It knows what the calibration dates were for what we call cycle resident. So that's the calibration file that was actually on the system when the M300 was flying. And also if there's a more updated, or what the latest available calibration file is, if you haven't actually updated the system that's on the cycle, that's cycle resident. But these are all aligned. They're from April of this year. And typically the default, of course, you always want to use the latest calibration file. So this keeps your system calibrated, making sure you're always using the most recent calibration information. The retained photos layer, basically similar to the LiDAR data. If I'm not interested in my transit legs or my turns or any particular part of my flight, I don't necessarily want to use the images from that portion of the flight. So I can basically create a layer that has just the photos I want to retain for my ortho photo generation. And typically we just do that within the flight lines, but you can keep them all if you want. And then we'll also update the EXIF tags on the photos, because we'll end up with a precise position here based on, again, the pause pack trajectory and so forth. So I can go ahead and create these trajectories. Again, won't necessarily run that just for time purposes. So once I've created my TrueView trajectories, I can move on to the next step, which is to geocode my LiDAR data to essentially generate my LAS point cloud. So I've got my raw LiDAR data that was recorded on the TrueView unit during the M300 flight. I now need to reduce that, put that into the reference frame of my project, and come up with my real world XYZ location. So we refer to that as geocoding. Not a lot that I need to worry about here as the user. Not a lot of options. Essentially, it already knows the flight lines that I want to use. I do have some clipping options. TrueView systems are 360-degree scanners, but of course you're flying on a drone, so you're really interested in a field of view that's plus or minus a certain amount either side of nadir. Obviously, you could make that as large as you want, up to theoretically, I guess, plus minus 90 degrees. But in practice, you're going to clip that back to something that's on the order of probably less than 40 degrees, plus minus 40 degrees. You can also clip by range. That can be useful in certain scenarios. This is where you say, anything beyond or within a certain minimum distance or beyond a certain maximum distance, I'm not interested in that. And that can be useful, for instance, when you're doing some scanning of vertical structures and so forth. We also have an option that we typically have on the by default all the time, what we call True Track, which is essentially swath compensation or roll compensation. So this takes into account the dynamics of the M300 in flight and tends to keep our, if we want to be plus minus 35 degrees on nadir, it tends to keep that on nadir. It removes any, if we have 2 degrees roll, it'll compensate that out when calculating the point data. And of course, we want to colorize the points. Now, our colorization in the TrueView systems, including in the 645 and the 650, is based on the oblique images, and it's using, it's a 3D colorization. It's using ray tracing to get the true color of the object that was hit. It's not a more traditional planimetric point in pixel type of colorization, where if you have an ortho photo, you just assign the color value based on the pixel of the ortho photo. The advantage, of course, is that the colorization is truer. You can get colorization on vertical structures and so forth. So it's a really nice colorization method. Again, I won't go ahead and actually run that, but we've seen the results, or I'll turn the results on here. And that will bring in our LiDAR data. There are a couple of additional steps that you want to do to the data. As with all LiDAR systems, there is a calibration that's been done. The system is calibrated, but there may be some residual dynamic error related to the positioning. You want to make sure that you have essentially got good alignment between your different passes between your strips. So this will be referred to as strip matching, strip alignment. It is, basically a little bit like a block bundle adjust in imagery, but basically want to make sure that all of our data is internally tied to the same reference frame, and we've removed any residual dynamic systematic error from it. That basically our flight lines overlap correctly on hard surfaces and so forth. Within LP360, we do that using strip align for Evo. So this is our licensed versions of strip align from Base Mapping. Very powerful tool. We've optimized it for the TrueView sensor, so it's very simple to use. When you're working through your project data, you essentially just need to tell it the particular LAS data, so the LAS layers that you want to feed into strip align, and basically give it an output layer name. So it's going to generate a new set of LAS files that have been properly strip aligned, so have had strip matching done to make them fit. I've already run it for this particular project. And basically, once that job finishes, it'll generate a new LiDAR surface for me, which has been strip aligned. The other step that you want to run on your data is you can both smooth and debias the data. So smoothing just removes any of the residual noise on hard surfaces. Now, for the 645 and 650 for Regal-based scanners, that noise is very small compared to what you would see with, say, a TrueView 515 or an automotive class LiDAR, and certainly compared to something like a DJI L1, right? The performance of a LiDAR system is often based on how good the quality of the laser and the receiver are that are integrated in the system, and that's partly what drives price. But one of the ways that you can tell, there are several, but one of the ways you can tell the difference in performance is by looking at essentially the fuzziness of the data, right? So if you look across a hard surface, we'll look at the road surface here. So we have some shot to shot, some peak to peak noise on a hard surface. And I'll just show you the results here. So if we look at our original source data here, and again, we're looking at probably about maybe 8 to 10 centimeters peak to peak there. And this is after we've applied that strip alignment, smoothing, and debiasing. And we're down in about the 2 centimeter range, something like that, 2 to 3 centimeters peak to peak noise. So those are quite important steps if you want to get the best quality data. So the last thing that I would generate before moving on to doing some of the product deliverables that we previously talked about would be the ortho photo. To do this, I'm going to use a DEM that I generated in LP360. So this is after I had done a ground classification. And I'm essentially just going to pass that DEM into Metashape. So we use a licensed version of Metashape called Metashape for Evo that allows you to generate your ortho photo. Submit this to our job manager. That job will go run. And when you're finished, you will have your ortho photo that you can import back into your project. And Metashape's a great package. We love it. It works really nicely. The final tool that I'll show you relates also to the imagery. So we have the oblique images from the 645 here, and it's very useful to use those. We have our LiDAR data. We've seen that, but we can also use our Image Explorer. Okay. And so Image Explorer lets me come in and collect, say, for instance, if I'm interested in this particular corner of this building, I can come in here, select a point, and my Image Explorer will drive to that location and find the nearest left and right images that can see that particular point. So here's my building here. You can see my satellite dish there. Here's my right image. I can see my satellite dish there. So from an inspection point of view, this gives the technician the ability to call up directly the most appropriate images for something they may be interested in or investigating or inspecting. For example, let's say I was interested in something on this intersection on the road here. I can pull that up. It'll automatically grab my nearest images, and I can come in here and make use of my oblique images as well. So very helpful if you have inspection tasks in your workflow where you can make use of the images. So at this point, we've really completed the processing flow for the TrueView data that's specific to the sensor. So we've taken the raw data that was observed during the flight, during the M300 flight. We've done our georeferencing. We've generated our colorized point cloud. We've generated our ortho photo. We have our obliques available. We can do our accuracy checking. But now we basically have a geo-corrected point cloud. We can flow into other downstream workflows. And one of the advantages of working with LP360, of course, is we have many downstream workflows and many sets of tools for working with point cloud that go back many years from working with our customers who are doing traditional LiDAR data. So you can flow this into, as I mentioned, power line workflows with data sets where you're looking at transmission lines. You can flow it into a volumetric workflow. You can flow it into just surface modeling. So we have a set of tools for doing brake line compilation. A lot of options as to where you go from this point, and having all of those options within LP360, it makes it fairly seamless to then move on to doing some additional value add work if you're doing that for your customer.
Thank you very much, Martin. That concludes our webinar for today. Thank you to all of our presenters for their valuable insight. We hope we've piqued your interest in TrueView 645, 650 and the DJI Matrice 300 RTK, as well as the considerable functions of LP360. If you have any questions or would like more information on our TrueView line of sensors, please contact us at info@goq.com. Thank you.